Welcome to Online Precalculus. This is section 3.1, Exponential Functions. Our objectives for this section are to evaluate exponential functions, talk about what is and what is not an exponential function. Then we will graph some exponential functions, both plain functions and one with transformations. Then we'll evaluate functions with the base e. And finally, we'll use compound interest formulas, which are a type of exponential function. So first, let's get into what the definition of an exponential function actually is. So the exponential function f with a base b is defined by f of x is equal to b to the x power. That's what makes this an exponential function. The variable is in the exponent. Okay. B has some restrictions though. B must be a positive constant other than 1, which means that B has to be greater than or equal to 0, and B cannot be equal to 1. And we can figure out why this is true, because if x is any real number, okay, and we have a base, right? Just say x is any real number. So the variable up there is 2. If we have a base of 2, this is no problem. A positive constant other than 1. However, if it's 0, right, change the exponent, right? Here's the exponent right here. Plug in numbers for x. You're never going to get anything but 0. Plug in numbers for x. You're never going to get anything but 0. The reason why this has to be a positive constant is because that's no problem, because if I raise a negative to a second power, I just get a positive number. This is no problem, because that just turns into a fraction. This becomes the issue, because fractional exponents mean square roots, so this would be equivalent to the square root of -2, which would not be real. Okay, so my restrictions there are all based on that logic right there, is that b has to be greater than 0, can't be equal to 0, and b can't be equal to 1 in order to make an exponential function. Again, these are all examples of exponential function. That's an exponential function with a base of 2. That one has a base 10. This one has base 3, and it has some stuff going on in the exponent. That's okay. Okay, it's just a transformation. Okay, same thing here. We have an exponent of x minus 1. That's okay. Fractional bases are okay. Capital F of x at the bottom is not an exponential function because the variable is not in the exponent. That's a quadratic. That's just x squared. Okay. This one is not, g is not an exponential function because it has a base of 1. This one has a base of negative, and this one has a variable in both the base and the exponent, which is definitely not normal. Okay. And this is from our discussion above, is if you have -1 to an x power, it's not an exponential function because you're going to get an imaginary number when you take the when you take a fractional exponent. Okay. In order to use these, you're gonna need a calculator. Okay. So most exponential functions, some you could do in your head, like if the base is 2 or if the base is 3. But once you start getting to bigger bases or decimal bases, you're going to need a scientific calculator that has some sort of exponent key. Sometimes it's y to the x, sometimes it's this, sometimes it looks like x with a box right there. Whatever the key is, and whatever type calculator you have, you're going to have to figure out how to use it to evaluate these functions. For instance, the exponential function right there models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent after 4 hours? So we're basically finding f of 4. So we're going to take 42.2, 1.56, and we're going to raise it to the 4th power. Remember, order of operations, the exponent comes first. So we get 42.2 times 1.56 to the fourth power is going to be 5.92. And then we just multiply by 42.2. Okay. This problem is not about, and we get 249.93, which it says round to the nearest dollar. So this would be 250. Okay. The setup is not hard, right? We have the equation right there. The trick is knowing how to do this, knowing how to plug it into your calculator. Okay. I don't think we need another one of those. So let's move on to some graphs. So you should be familiar with expressions involving b to the x where x is a rational number, like a integer or a decimal like 1.7. If you wanted to evaluate 1.7 and you didn't have a calculator that had a button, you could turn it to a fraction, 17 over 10, which means it's the 10th root of b to the 17, and so on and so on. But x, when we're talking about these exponential expressions, x can be any real number. So you may be curious if rational exponents are okay. So can you have b to the radical 3? Can you have b to the pi power? Sure. Estimate it. Use a decimal. Okay. Even your calculator might be able to plug something in. The point of this is just to realize that because x is able to be anything, because the domain is all real numbers, there are no holes or discontinuities in exponential functions at all. Has some other properties, which we'll look at as we do this graph. Okay, so in order to graph this successfully, just make a table, right? Let's plug in some negative numbers and let's plug in some positive numbers. Okay, well, 2 to the negative third power is the same thing as 1 over 2 to the third power. Negative exponents give you fractions, so this is 1/8. 2 to the negative 2 power is 1/4, 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the first is 2, 4, and 8. So we sort of see this pattern here where the denominators are all, or sorry, the numbers down here match the denominators up here. Okay, that's what happens when there's no transformations on these functions. Now let's graph it. We got 0, 1. Let's start going to the right. 2, 4, 8. We could even plug in 4 here. 4 squared is 16. And we have a couple points that way. Now, if you notice what happens when you go to the left, we get 1/2, a quarter. These get harder and harder to graph. A 16th, a 32nd, 64th. But you see that no matter what number goes down here, right? 2 to the 10th is 1 over 1024, hundredth, thousandth, whatever. You are never going to get a negative number. Okay, negative exponents just give you fractions, which means this graph is never going to cross the x-axis. Okay, which means we can say a few things about the end behavior. Okay, on the left end, we can say that the limit as x approaches negative infinity of my function is going to be 0. That this function flattened out. As I go left, the function flattens out to a horizontal asymptote. But the right side does not approach a horizontal asymptote. In fact, the limit as x approaches positive infinity is going to be infinity. Okay, so this is a different thing that we did than the rational functions when the left side and the right side were approaching the same number, a horizontal asymptote, and the graph just jumps straight up and down at some vertical asymptotes, at some infinite discontinuities. With these functions, one side is going to go flat, the other side is going to go up or down. Let's graph another one. Okay, again, simple as making a table And again, let's plug in a couple of negative numbers. This one's going to go up a lot faster, so 3 is going to even be off the chart here. 3 to the third power is 27, so that's 1 over 27, 1 over 9. Anything to the 0 power is 1, 3, 9, 27. And you can see that it's slightly different. 9 and up 27. The left side, it's harder to tell, 1/3, 1/9, but it still goes kind of flat. Okay? And while these graphs do look similar, right, they are slightly different, right? This point is the same, but these next points are definitely different, and they're not going to be related to each other. So unlike other functions, exponential functions don't necessarily have a parent, one parent. In fact, every function that looks like this, that is just a base to an exponent, is its own parent function. Let's see the difference with this function when we have a fraction in the base. Okay, so as I plug in my negative numbers, remember that negative numbers usually give you a fraction, but if you raise a fraction to a negative third power, that makes 1 to the negative third over 2 to the negative third, okay? And means they switch, so that's 2 to the third over 1 to the third, which is now 8. So if you put a negative number, if you raise a fraction to a negative exponent power, it turns into a number bigger than 1, okay? So this would be our 4. That's our 2. Anything to the 0 power is 1. 1/2 to the first power is 1/2, 1/4, 1/8. So you can see that this graph sort of behaves the opposite, 8 and then 16. This, whoops, 16 goes right there at 3. -1, -2. Whoops. Okay. So a little off there. -1 is 2. Skip 1. There we go. 2, 4. -3 is 8. -4 is 16. Okay. Then as I go to the right, we get my slowly shrinking graph. Let's try to graph this with a nice smooth curve. And we see a similar pattern to the previous example, but now the limits are reversed. The end behavior is reversed. The limit as x approaches negative infinity of my function is infinity, and the limit as x approaches positive infinity of this function is 0. Okay. And same thing with a 1/3. And again, one thing to notice here is that, well, 1/3 could be 3 to the -1 power. Power to a power, you multiply the exponents. So 3 to the negative x is actually the same graph as 1/3 to the positive x power. Okay? In fact, this is a way to represent a reflection of 3 to the positive x in the y-axis. Okay, so we could just graph this again. -3 is going to be 1 over 20. Whoops, is going to be 27. And we can even plug it into this one. Negative times a negative is positive. 3 to the positive 3 is 27. -2 would be 9. -1 is 3. 0, anything to 0 power is 1. 1 would be 1/3. 1/9, 1/27. Okay, and 27 is not on this graph. It's a little bit off. So we'll graph 9, 3, 1, and then this graph falls off very quickly. And missed the graphs, missed the points there a little bit, but we get the idea. Okay. And again, Notice that these graphs are going down from left to right, as opposed to the graphs on the previous page, which were going up from left to right. Okay, so let's talk a little bit about that right now. So here are 4 exponential functions that have been graphed below. So if you look at the black and the green graph, look at the base. The base is a 2, the base is a 7. However, look at the blue and the red one, which have bases that are less than 1. So we can say that when the base is less than 1, the functions are going to go down from left to right. When the bases are bigger than 1, they're going to go up. Also, notice that the bigger bases here make the function steeper, while bases closer to 1 make the function flatter. And remember, the base cannot be negative. Okay. In all these cases, they have the horizontal asymptote at the x-axis. So here are some general characteristics of exponential functions that we could have observed in the couple graphs that we did. Okay. First is that the domain of these functions, the domain of b to the x power, is all real numbers. There is nothing that you are not allowed to plug in for x. However, the range, the outputs are going to be restricted. In this case, if you just have a plain base and the variable in the exponent with no transformations, the range is going to be from 0 to 1, or sorry, from 0 to infinity, not including 0. The graphs of all exponential functions in this form are going to have 0, 1 as a point, because anything to the 0 power is going to be 1. Okay, so the y-intercept will always be 1 if it is just a base to an x power. Okay, there is no x-intercept because it's a horizontal asymptote. If b is greater than 1, the graph goes up to the right, and it is an increasing function. In fact, it is called exponential growth. Okay, the greater b, the steeper the increase. Okay? If the base is between 0 and 1, remember the base can never be negative, the graph goes down to the right, and it's called exponential decay. The smaller the b, the steeper the decrease. Okay? The closer it is to 1, the flatter it is. This function is 1 to 1. It passes the horizontal line test, which means it has an inverse that is also a function. That inverse actually is a logarithm, and we'll cover that in the next section. The graph approaches but does not touch the x-axis, making x a horizontal asymptote. Now, like every other function that we have graphed in the past, it is possible to translate these functions vertically, horizontally, reflect, and stretch vertically and horizontally, right? We can move them up, down, left, right, reflect over the x, over the y, and stretch and compress vertically or horizontally. Remembering where these numbers make those shifts. So a positive c shifts up, a negative c outside the exponent shifts down, a positive c in the exponent shifts left, negative c in the exponent shifts right, a negative in the front reflects in the x-axis, negative up top, we just saw that reflects in the y-axis. Numbers in the front stretch the vertically if it's bigger than 1, shrinks it if it's between 0 and 1, negatives reflect, and then numbers in the exponent, constants in the exponent, shrink if it's bigger than 1, stretch if it's between 0 and 1. So we can do all of those transformations on any of my exponential functions. In fact, let's try one like this. Okay. And again, unlike previous functions where, well, we could do this. We could use this graph. Let's graph this one, and then we'll shift it to get this one, and then we'll talk about how to do it without going through that. Okay, so if I'm going to make a table for 3 to the x power, right? We graphed that before, right? So it's -3, -2, -1, 0, 1, 2. These are my fractions. 1, 3, and 9. Okay, so I would just graph that 3, 9, 1/3, boom. So I would get my graph to look kind of like this. Okay. If I wanted to graph this as a transformation, let's try to get another color here. Get red. If I want to get this as a transformation, if I want to shift this 1 to the left, I could take all of these points and shift them 1 to the left. It gets harder and harder to tell as we get closer to the x-axis, but we can see that my graph goes up a lot steeper as I get, all my points have been shift 1 to the left. Now, did I have to do that? It might have been easier just to jump right into this function and graph that function by itself. For instance, right? Let's just graph 3 to the x minus 1 power. So just make a table. Okay, so we have my x, we have my y. We still have to plug in negatives. We still have to plug in positives. I should realize that this function is going to shift to the right this time. Okay, and as I plug in -1, that becomes 3 to the -3 minus 1, which is 3 to the -4. So that's 1 over 4th power, 81. -2 becomes 1 over 27 now. -1 becomes 1 over 9. 0, remember this isn't this isn't 3 to the 0 power. It's 3 to the 0 minus 1 power. So there's my 1/3. 1 becomes 1. 2 becomes 3. 3 becomes 9. And then we'll go be off the graph with 27. Okay, so I usually like to start graphing the term that gave me a 0 as an exponent first. And I think that it just makes that a little bit easier. 2, 3, 3, 9, right? And then we get our 1/3, 1/9. Then we get closer to the x-axis as we go to the left. So there's my graph of that transformation. We already talked about that. Slide was in the wrong place. That's okay. So if we have a number on the outside, now that shifts the function down 3. So again, might as well just make a table for this. Plug in your numbers, and we're gonna need some you're gonna need some negative numbers, yeah. Ooh, this is actually a bad graph. Okay, we're gonna need a little bit more room down here. Okay, 1, 2, 3. Okay, so when we graph this one and we shift the function down 3, okay, all of my points are going to be down 3. So I'm going to have a horizontal asymptote that no longer is the x-axis. It's going to be -3. In fact, when I plug in 0, I get, sorry, it's going to be negative. Yeah, -3. 2 to the 0 power is 1. 1 minus 3 is -2. All right, plug in 1 there. Get 2 to the first is 2. Minus 3 is 1. -1. Plug in 2. We get 4 minus 3 is 1. There we go. Plug in 3. We get 8 minus 3. It's 5. Plug in 4. And now we get 2 to the 4 is 16. 13. Plug in 5. Can we fit 5? 2 to the 5th is 32 minus 3 is 29. Not quite. Okay. So I usually like, I know that the other ones are going to be fractions. Okay. But I don't want to subtract 3 from them. So I'm just going to start with this. 0 would be -2. So that's right there. 2 would be, 1 would be -1. 2 would be a +1. 3 would be a +5. 4 would be a +13. Okay, and then the other one's off the graph. And then I know what's going to happen here. This is going to go halfway between there, and then it's eventually just going to go flat towards the x-axis, never touching, never crossing. Okay? So I think that is good with transformations. This one would just shift that same one up. Should have graphed that one instead, but let's talk about E. Okay, so in our number system, the most common base for an exponential function is 10 because it should make sense. Every digit in our number system is a power of 10, so that is really the most common base that we have. However, there's an irrational number symbolized by the letter E that appears in many applied exponential functions, stuff that models growth or decay that is always happening. So just like special irrational numbers, like take pi. Pi is a ratio between a circle's circumference and its diameter. Very, very specific thing that is talking about. So is E. E is defined by this fraction, but it's defined as the limit of that fraction as n gets bigger and bigger. So you can see what happens with this, with these values. If n is 1, you plug it in, you get 1 plus 1 over 1 to the 1 power is all 2. You plug in 2, you get a decimal, 2.25, and you start getting numbers that are closer and closer as n gets really, really big, like a billion. Your number gets closer and closer to this number E. So we can say that the limit as n approaches infinity is E of this function. Okay? E represents this decimal, 2.718281827. And if you look at it, if you bring it out to some more places, if you look it up, right, it actually has some weird patterns there, a lot of 8 7s, and you can see a little pattern here with the first couple of letters of E. First couple numbers of E. But like pi, we usually approximate it to just 2 decimal points. So 3.14 for pi, 2.72 for E. This is called the natural base. It's called the natural base because it works so well in these applied exponential functions that model the natural world. Okay, so the function E with an exponent is called the natural exponential function. And most scientific or graphing calculators have this button to help you evaluate E. Okay, you're gonna have to be able to find it just like we found the other function or the other button to do random x's. We're gonna need to find the button for E to the x power. It might be close to a button that has a log or something that has an ln. Okay, might have to press shift, it depends on your calculator. If you wanted to do E squared, you should get something like 7.389. Okay, so the number E lies kind of between 2 and 3 is 2.72. So because 2 squared is 4 and 3 squared is 9, it makes sense that 7.39 is E squared. And because E is between 2 and 3, the graph of E to the x power is going to be sort of this red one that's kind of between E squared, or 2 to the x power and 3 to the x power. Still going to have a horizontal asymptote. It's still going to be steeper than 2 to the x, but not as steep as 3 to the x. Let's try a problem with E. Again, this problem is a longer word problem, but It's just to make sure you know where E is on your calculator. So gray wolves. Insatiable killer. That's the reputation of the gray wolf acquired in the United States in the 19th and early 20th centuries. Although this label was undeserved, 2 million wolves were shot, trapped, and poisoned by 1960, which means the population was reduced to 800 wolves. So this figure shows the rebounding population in the recovery areas after the gray wolf was declared an endangered species and got federal protection. So they're trying to grow the gray wolves back here and here. That's not as important as look at the way these graphs are going. They kind of look like exponential functions. And in fact, here is the function that models them, and it models it using the, not the variable e, the irrational number e. So this function models the gray wolf population of the northern Rocky Mountains X years after 1978. So if it's not removed from the endangered species list and these trends continue, find how many wolves are in the area in 2010. Well, if X is the number of years after 1978, all we have to do, well, here's my function, f of x is 1.26 e to the 0.247 times x. All we have to do is find f of 32. 2010 is 32 years after 1978. So that's 1.26 times e to the 0.247 times 32. Remember that, well, sort of parentheses come before exponents, right? So you're going to have to multiply these two together first, then the exponent, then e to this power, and then multiply by 1.26. Hopefully your calculator gets that, and you should get about 3412. Okay? And then some decimals, but we can just round that down. Okay. Let's look at the next problem. So again, just a way to practice plugging this into the calculator. So again, years after 1978 to 2012, that's 34 years. So we would find f of 34 is going to be 1066 times e to the 0.042 times 34. Plugging this into your calculator gives you 0.042 times 34. Around, we can round this up, 4,446. Yeah, 0.6, so we can round that up. Okay. One of the more useful things to use exponential functions for is to calculate compound interest. Okay. In fact, it is an important part of having financial independence and financial security, saving your money and letting it compound in either some sort of savings account or even better, something like the stock market. Okay. So compound interest is interest computed on your original investment as well as any accumulated interest. So you make some interest the first year that you are saving your money, and then that money is now yours, and now you earn interest on your original money plus the interest that is now yours. That is called compounded interest. Some vocabulary: a sum of money, the original amount you start with, is called the principal. If it is invested at an APR, annual percentage rate, usually denoted as R, always in decimal form, compounded once a year, we can look at this equation. Okay, so because the interest is added to the principal at the end of the year, our accumulated value, right? Accumulated value is my variable A, is always going to be the principal plus principal times your rate. I can factor out that P to get my equation that looks like that. And then if I keep doing this every year, right, I get another 1 plus R. Well, now I have 2 of them. I get another 1 plus R. Now I have 3 of them. Now I have 4 of them. So you get this equation that gives you the balance of a principal, T years at an interest rate compounded once per year. Okay, well, there's a problem with that formula. And that is that life doesn't really, our financial situation, our financial institutions don't really calculate interest once per year. Most of them do it by month. You think about your credit cards, your loan payments, your whatever it is that you are getting interest for. Usually you get that, or you get a bill for it once a month. Very rarely will there be something that only gives it to you once a year. In fact, you're missing out if you are getting the interest, and the company, if they're charging you the interest, is missing out as well. So many places have plans which interest is paid more than once a month. We have some words for that. Annually means twice a year, or sorry, annually means once a year. Semi-annually means twice a year. Quarterly means 4 times a year. Monthly means 12 times a year. But no matter what, the number of compoundings that we are going to do depend on just the wording of the question. And we say that interest is paid n times per year. So we can now adjust our formula. We can adjust this formula that has a yearly interest rate and a yearly time, and we can adjust it based on the number of compoundings they are in each year. So we change our interest rate to, say there's monthly compounding. We change it to a monthly rate by dividing the yearly rate by 12. But that means we also need to multiply the exponent by 12 to change it to months, if we're talking about months. We can keep this very general with this formula right there. But now, if you do this all the time, think about n, right? Compound once a month, compound once a day, compound once an hour, a minute, per second, every half second and quarter second. So you can keep compounding more and more and more. And then you get to something called continuous compounding, where the number of compounding periods increases exponentially. And if you look at what happens here, right? If we take our original formula, right, we just switch this exponent to something that looks like this, right? It means the same thing. Okay, power to a power, I can do that. I can put parentheses around this. Now, if we look and we move r to the denominator by just dividing by their reciprocal, these two are the same. So as n over r gets closer and closer and closer to infinity, right, we can say, well, that kind of looks like this, which I know from before, if 1 plus 1 over something to the same power, if it keeps getting bigger and bigger and bigger and bigger, if your compoundings keep getting bigger and bigger and bigger and bigger, and this number, the interest rate's not changing, keeps getting bigger and bigger and bigger and bigger, this expression goes to infinity, which means it is equal to E. Here's a new formula. P E to the RT power. And that works when we have continuous compounding. And even though this sounds like it is going to give you a lot more money, it is really only a couple, maybe a couple cents, a dollar or so more, depending on how long you're talking about. Okay, really not much more, not much better than daily compounding, but a different formula that we're going to have to use. So here are the two formulas to focus on for compound interest. The first one is when you have n compoundings, a number of compoundings. Doesn't matter what that number is, okay? As long as there is a discrete number of compoundings per year, okay? And we're going to break this down by year. If you see this word, continuous compounding, that means that we are going to use a lot of people call it the PERT formula, P-E-R-T, okay? Just remember the RT is an exponent. Let's see how these work. So you decide to invest $8,000 for 6 years, and you have a choice between two accounts. So let's break this down. Here's account 1, here's account 2. Okay, there's my principal. There's my time. The first pays 7% a year, compounded monthly. Well, that is a number of that is a discrete number of compoundings per year. So I'm going to use my first formula. So my principal, well, let's just write it down first. So this is P times 1 plus R over N to the NT power. My principal is $8,000. That's 1 plus my interest rate, always as a decimal. 7 is a percent. Change it to a decimal, 0.07 over 12, because it's monthly compoundings, to the 12 times 6 power. Okay. Parentheses first. So we're going to do the inside of those parentheses before I do the exponent, and then we are going to multiply the answer by 8,000. So let's go take this a little bit slower. 1 plus 0.07 over 12 gives me 1.00583. And you're going to want to try to keep that as many decimals. In fact, it's better to even just leave it in your calculator. So that way you get as accurate a number as you can. Okay, so this would be 12 times 6 up there. Okay, and we would get that now this is 8,000 times 1.52, and it gives us a total of $12,160, and always 2 decimal points with money unless you are told otherwise. Okay, now let's compare that to the second account, which is compounded continuously, different percent rate though, lower percentage. Okay, so even though you're compounding more often, you're going to get less of a percent. Not much less, but it will make a difference. Here's my formula. My principal is still 8,000. E is not a variable. It is a irrational number. It's just a number. Change this to a decimal, and it looks like it's a decimal, but it's still a percent. So we need to change it to 0.0685 times 6. Okay, making sure we know how to do this on our calculator, and this gives us 12,066.60, which makes the first account more money. Compounded less often, but still gives us a greater return in the end. Let's try one more. Okay, so again, we have two different situations here. We have my first one, which is $10,000 compounded quarterly. Okay, so that's 1 plus 8%, 0.08 over 4, 5 years. So 4 times 5. Okay, calculating this, and this one is good because nothing else changes except for the compounding, so we can see what the effect is of the continuous versus the quarterly compounding, with everything else being the same. Okay, so this one we get $14,859.47. For the continuous compounding, that's 10,000. E, same rate, 0.08, 5 years. Okay, we don't have any other thing that we need there. So 10,000 E 0.08 times 5. And notice that we still get 14,918 and 25. So, what is that? 50, 60 bucks or so? Like the text said before, if I change this to daily, right? If I made this 10,000 times 1 plus 0.08, 365 to the 365 times 5. Okay, if I compared these two, what you'll notice is, let me just get this answer here, 0.08 over 365 to the 365 times 5. Notice you get 14,917 and 59 cents. Okay, so daily compared to continuously is going to only give you, not even $1 more. Okay, but definitely makes a difference compared to something like quarterly. But once we get down to a daily compounding, there really is much less of a drastic difference. But continuous compounding, if everything else is the same, continuous compounding will always be more. And that is section 3.1, exponential functions.